Something we want to start doing is relating the derivatives that we're taking with graphs of the function. And what this will do, it'll let us talk about where we're reaching minimum values and maximum values, which are so important for word problems. We're trying to minimize or maximize something. And that's where we're headed with this idea of optimization. Another important idea is the idea of increasing, decreasing. So when is our rate of change positive and when is our rate of change negative? That can be important for context as well. So here we have three graphs. We have our original function, our derivative function, and our second derivative function. And notice that we see this change of something cubic to quadratic to linear. That's part of our power rule for taking derivatives. We always decrease the power by 1. So if we have something cubed, if we bump it down by 1, we end up with something quadratic. Bump that down by 1, we end up with something linear. So this is just a kind of a visual that goes nicely with that. So let's talk about some things that we're seeing here. Over what intervals is f prime of x more than 0? So I'm going to do a zoom in on our first derivative function here, and I want to see where is this more than 0, which basically means where are we above the x-axis. So it's happening in two spots. We're seeing that in values from the left of -1. We're also seeing it for values to the right of +2. So we have two intervals from -infinity to -1, and we're not going to include -1 because we're looking for strictly more than, not equal to 0. And then a union with the interval from 2 to infinity. So now what we're going to do is go to our original function, f of x, and look at those same intervals. So we're seeing from that -infinity to -1 as this piece of our function. And then from 2 to +infinity, we're this part of our function. We want to know, what are we seeing there? Well, what we're seeing is that our function is increasing. It's getting larger and larger and larger until we hit that peak right there. Then our function's decreasing, and that's part that we're not including in our interval. And then when we reach this minimum here, we switch back to increasing. So for both of these intervals, we're seeing that our function is increasing. So where f prime of x is more than 0, what is true of f on this interval? F is increasing. So we're seeing this rate of change of f where it has a positive rate of change, which means f prime is positive as well because of that positive rate of change. Okay, let's look at some more scenarios here. Over what intervals is f prime of x less than 0? So now we're going to switch this up to look at below, which below the x-axis is the bottom of the parabola right here. So we're seeing the interval from -1 to +2. And what is true of our original function on that interval? So -1 to +2 for x. This is where we're starting at that maximum value, and then we're going down to that minimum value. And what we're seeing is that our function is decreasing over that interval, and our function is not decreasing anywhere else. We have that increasing part, then we go to decreasing, and then we're increasing again. So for that interval, our original function is decreasing. So how I kind of think of these is moving backwards like this, looking at our original function. We're thinking about something standing still, kind of this still frame picture of, are we positive? Are we negative? Here what we're thinking about is movement over those intervals, relating those two. So where we saw those positive values for our derivative, it isn't about just those locations, it's about moving along our function. So it's like we're moving and seeing how are we moving. So there's kind of movement in the early graphs, where in the later graphs we're kind of looking at a still picture of it. Okay, over what intervals is f double prime of x more than 0? So now we're going to our second derivative functions, our linear, and it looks like we are above 0 for values from, let's go ahead and say 0.5 onward. So our interval is 0.5 to positive infinity. And we're going to look at this over f prime, which we see that right here. And we're going to look at this on our original function. So 0.5 is about right here and over here. Okay, so let's just talk about second derivative function going to first derivative, because how this is going to relate is just like how we talked about our first derivative and original function, kind of going in that same backward direction. So where our second derivative is positive, if I go to my first derivative, that's where our function is increasing. On the left-hand side, our function is decreasing. So from that interval 0.5 off to infinity, if I want to know what is true of f prime on this interval, f prime is increasing. Now let's go to f, which we haven't done yet, of going back 2 spots. So if I look at just my function of f of x for that interval from 0.5, let's go ahead and say that's right there. This is where we talk about concavity, concave up versus concave down. So concave up, just as a refresher of our work with quadratics, concave up is a parabola that opens upward. Concave down is a parabola that opens downwards. So what we're seeing on our graph here is that we have a mixture of concavity. We have concave down, and then it changes to concave up. And what we're seeing is the interval that we're talking about right now is concave up. So what that tells me is that when the second derivative is positive, our original function has a graph that is concave up over that interval. So what is true of f on this interval? F is concave up. And now if we do the same thing for the negative portion, so from negative infinity to 0.5 is going to be our interval. And what we're going to see is just the flip of all of these. I can go ahead and plug this in of f prime is going to be decreasing, and f is going to be concave down. So I can see this if I go back up here, because from negative infinity to 0.5, my function is going downward until we reach that minimum value where it switches. And then here, we're seeing this left-hand portion, which is a parabola opening downward until it flips to the other direction. So we're seeing concave down right there. So something we're going to talk about in future videos are these kind of key changing points. When we're talking in terms of concavity, this is called the inflection point. Then we have these turning points like at the bottom of the parabola here, and we're going to call this a critical point. We have it on our first graph too. We have 2 turning points, so both of those would be critical points as well. And then we'll even go as far as describing them as minimum maximums. So like that critical point right there at the top of kind of that peak, that would be called a local maximum. Even though it's not an overall maximum for our function, just in that little spot there, if you kind of think in a zoomed in sense, we are reaching a peak, a maximum value right there. Similarly, down here, this would be a local minimum, because it's just a little, peaks and valleys is what I think of, but minimums and maximums work as well. Okay, so talking through all of that, what we're getting at are these big properties right here. Our first derivative tells us about increasing, decreasing. Where our first derivative is positive, we're increasing for our original function, and where f prime is negative, decreasing for our original function. Then second derivative is going to tell us about concavity. When our second derivative is positive, our original function's concave up on that same interval. Where our second derivative is negative, it's concave down on that interval. What this will do is the derivatives will help us get a general idea of the shape of our function, and even sometimes not even needing a graph to evaluate these properties.